Welcome to The Explainer. Today, we're investigating what honestly feels like a massive, impending crisis in the world of microelectronics. And more importantly, we're exploring the absolutely revolutionary shift toward computing with light.
Seriously, what happens when the fundamental laws of computing just break? For decades, our digital world has relied on this steady, predictable march of progress. But right now, modern workloads are pushing our highest performance computers to their absolute breaking point.
Section 1. The Silicon Breaking Point. Okay, let's dive into exactly why the hardware we rely on every single day is suddenly struggling to keep up. For over 50 years, microelectronics have been guided by Moore's and Dennard's laws. That's essentially the prediction that computing power and efficiency would exponentially double roughly every 18 months. But here's the catch. These empirical scaling laws are finally hitting fundamental physical limits. You literally just can't shrink transistors forever. At the exact same time, our modern workloads are demanding unprecedented resources. Think about the massive artificial intelligence tools we're all suddenly using daily, or those incredibly complex climate simulations. They require a staggering amount of processing power. Traditional digital electronics are proving to be inherently inefficient for these kinds of heavy, distributed, parallel computing tasks.
Section 2. Dawn of Photonic Computing. So, with silicon essentially maxing out and quantum computing still being years away from commercial scale, a new contender is stepping into the gap. Photonic computing, also known as optical computing, is the use of light waves, specifically photons produced by lasers or other light sources, to perform computations instead of electricity. Now, researchers have actually explored this concept for decades, but it's finally stepping into the spotlight. Why? Because it offers a massive, game-changing upgrade over traditional electronics. Specifically, we're talking about much lower latency, way higher bandwidth, and massive parallelism.
Let's track how this has built up over the decades. Way back in 1976, the very first optical transistor was proposed. Fast forward to the 2010s, and facing absolutely incredible demands on GPU accelerators, the focus shifted heavily to on-chip integrated optics. And look at where we are now. By 2025, photonic computing officially enters the Gartner hype cycle for data center infrastructure technologies. So this maps a really clear trajectory from pure academic theory to a highly practical technology gaining serious, real-world traction with industry leaders and investors.
The core advantage here really boils down to two things: heat and speed. See, electronics rely on electrons. Electrons generate a lot of heat, and they have a highly limited drift velocity. They basically drag. Photonics, on the other hand, utilize photons. They operate in low-energy environments with minimal thermal overhead, meaning you're wasting way less energy on cooling down massive server farms, and they transmit data at the literal speed of light.
Section 3. How light computes.
So how does calculating with light actually work? Well, there are three primary architectural approaches. The oldest form is free space optics. This literally manipulates light right in the air or in a vacuum, using lenses and spatial light modulators. Moving into much more compact forms, we have photonic chips. These miniaturized components like lasers and interferometers, so they fit directly onto silicon for speed and easy integration. Finally, we have optical fiber systems. These harness guided light within fiber optic loops to perform complex calculations, cleverly leveraging the communication infrastructure we basically already have in place around the world.
But, researchers have also come up with incredibly creative, frankly unconventional ways to calculate. For example, using optical fibers to delay light signals can actually evaluate multiple solutions all at once, which is perfect for solving complex math puzzles known as NP-complete problems. Other methods use entirely different wavelengths of light to represent different variables. There's even a wild approach that evaluates truth tables by making photocopies on transparent sheets and overlapping them to find a solution. It's really out-of-the-box thinking.
To give you a sense of the sheer scale of modern engineering here, consider the number 1052. That is the exact number of integrated optical components that Hewlett-Packard Labs successfully packed into a single chip Ising machine. And an Ising machine is basically a specialized computer designed directly around the theoretical physics of the Ising model. That is a ton of optical hardware on one single chip.
Section 4. Overcoming optical bottlenecks. Despite all this immense promise, we do need to be impartial and look at the actual technical hurdles standing in the way of commercialization. The absolute Achilles heel of current systems is the OEO conversion penalty. Because it's still really difficult to store memory optically, systems constantly have to convert signals from optical to electronic and then back to optical again.
This constant switching consumes about 30% of the device's energy and severely slows down data transmission. It effectively destroys the inherent speed advantage of light in the first place.
Engineers are basically fighting an uphill battle against physics on a few main fronts here. First, light-based systems are super vulnerable to slight misalignments, temperature changes, and random signal noise. So precision and stability are massive hurdles. Second, there's a distinct lack of built-in memory, like optical flip-flops. And on top of all that, physically packaging these miniaturized 3D circuits is an incredibly complex integration challenge. To fight this, researchers are experimenting with advanced materials. For example, using lithium niobate for optical interconnects, which is aimed at drastically reducing both signal loss and noise.
It's also worth pointing out there's genuine debate in the scientific community regarding fully optical computers. As critics rightly note, real-world logic systems require logic-level restoration, cascadability, fan-out, and input-output isolation, all of which are provided by electronic transistors. Simply put, electronic transistors are incredibly cheap, low power, and highly reliable. If optical logic wants to truly compete outside of a few niche applications, we are absolutely going to need major breakthroughs in nonlinear optical device technology.
Section 5. Impact on artificial intelligence. Okay, let's pivot to see how photonics is already revolutionizing the exact workloads that are currently breaking silicon. Look at this number, 72 femtojoules. That's practically nothing, but that is the incredibly tiny amount of energy an integrated bio-inspired spectrum slicing photonic chip requires to perform a single multiply and accumulate operation. The energy efficiency here, when you compare it to traditional digital electronics, is absolutely staggering. And then there's the processing speed. A recent breakthrough introduced an algorithm known as POM-MM. That stands for Parallel Optical Matrix-Matrix Multiplication. Here's how it works. Input is first encoded via a spatial light modulator. This allows direct tensor processing to happen using coherent light. And the result? Single-shot matrix multiplication. You can perform massive tensor operations, which, by the way, are absolutely crucial for deep learning, in a single high-speed shot of light. It's a direct challenge to the dominant role of conventional GPUs.
Researchers are also building hardware-friendly photonic systems using mature V-cell lasers. Those are actually the exact same ubiquitous, cheap lasers you'd find in fiber optic transmitters or even in your mobile phone. By mimicking brain-like neuronal optical spikes and using a really novel binary weight significance training scheme, these optical spiking neural networks process information at ultra-fast gigahertz rates. In testing, they achieved over 94% accuracy on the complex Madelon dataset, and they did it with radically reduced training times compared to traditional models. It's a huge step forward.
Section 6. The future of hardware.
Let's look at how all of this builds towards the ultimate commercial roadmap for our hardware. The immediate reality is that before we reach some sci-fi world of fully optical processors, the near future firmly belongs to hybrid systems. Combining optical and electronic components provides the most feasible near-term solution. It lets us leverage the incredible speed of light while still relying on electronics for the things optics struggle with, slowly working to eliminate that conversion penalty over time. And there are several bleeding-edge innovations to keep an eye on that aim to solve those scaling and memory bottlenecks. For one, optical cavities that can actually use light as both the memory and the compute medium simultaneously. We're also seeing simplified Mach-Zehnder interferometer meshes, or MZI meshes, which drastically reduce the number of phase shifters you need, making chips super space efficient. Finally, engineers are integrating closed-loop machine learning feedback. This automatically ensures laser stability and precision, basically making optical systems robust enough for daily commercial data center use.
Which leaves us with one final fascinating thought. As silicon reaches its absolute physical limit, will the ultimate future of computation be written entirely in light? This technology offers a profound shift in how we process information, and it's a field moving faster than ever. Thank you for joining me on this explainer.